We are going to wait some minutes and we start. Good morning, Marco. Hello, everyone. We are going to wait some minutes. Okay, so I think we are going to wait 1 minute more because we are waiting to the participant, and we start. Okay, so welcome and thank you everybody for coming here today. Welcome to the webinar Groundwater Facing a Common Challenge 2022, organized by Cetaqua in collaboration with the Universitat Politécnica de Valencia and the University of Pavia. During the interventions, please keep your microphone off. If you have any question, please ask them by the team chat. So welcome everybody. It is a pleasure to be here for another year. This webinar is the second part of the webinar we did last year with the same participant. In this case, we are here to talk about the results and the progress that all the projects have been made. I will leave the link of another webinar in the chat. And now I present my colleague Damian Sanchez from Cetaqua.
Hello, thank you, Bea. Good morning, everyone. First of all, thank you for joining this this webinar on groundwater management and governance. So I would just like to very quickly to put some context on this webinar. So the webinar, as Beatriz told us, is the second webinar we organized. The first one was last year, and this is the second one. The webinar is organized by the 4 projects awarded in the 2019 PRIMA call on sustainable groundwater management. So the idea was to create a common space or framework to discuss about groundwater governance, groundwater management, how we can improve it, what we are doing to improve this groundwater governance, and with the final objective of, I think this is a common objective of all projects we are going to present today, to guarantee a sustainable groundwater management, something that right now is not a reality in all groundwater bodies at European level. So we think that there is still room for improvement. So this is the reason we have these 4 projects, these 4 ongoing projects. So that's all. So I think you will enjoy the webinar, and okay, I hand over the word to you, Bea.
Okay, Marco, if you want to present the webinar, can you hear us? No. Marco cannot hear Damian or me.
I saw some messages saying that they couldn't hear me so well.
He is a moderator.
Oh.
Okay.
Marco, can you hear us now?
I think no. Can you hear us?
Let's see if we can hear his microphone.
Yes, if he can speak.
Can you hear me?
Yes.
Yes.
Oh, now
okay.
It works.
All right.
Okay.
So do you wish me to give the introductory remarks and then try to solve this issue? At least you can hear me. Yes.
Yeah. Now it's okay.
Okay.
Yeah.
All right. Okay. So I hope that I will be able to fix this problem, because I seem to hear the notifications when someone joins the meeting room. So it's not a problem with Zoom, but for some reason I cannot hear Beatriz and Damian when they speak. All right, okay, let's start the meeting anyway. The show must go on, and then we will fix this later. Let me just introduce myself very quickly. My name is Marco Orlando, and I am the project officer responsible for the water management thematic area at PRIMA. Good morning to everyone, and thanks a lot for the effort that the projects made today to be here. Thanks also for the invitation, this opportunity to give some introductory remarks. Again, I would like to thank the Cetaqua team for convening the webinar, and also the other projects, the coordinating teams from Università di Pavia and Università Politecnica di Valencia. Of course, also the other partners that are in the meeting room today, following, and all the researchers and colleagues that are following from home. Okay, just I would like to remind you that this is the second webinar. It's a follow-up to a previous one on groundwater management, which was organized last year by these by the 4 projects. A very important theme that today we will be discussing again with several presentations. Of course, these projects are funded by PRIMA, the Partnership for Research and Innovation in the Mediterranean area that some of you may know already. This is an R&I funding program that was launched 5 years ago, and with the aim to bring together 19 participating states and the European Union to create kind of an alignment of their research priorities, while at the same time using research and innovation as a tool to address the common challenges faced by the Mediterranean countries, like, for example, water scarcity, the effects of climate change, food insecurity, and so on. So again, today the topic is groundwater management, and the related challenges. We know that this year groundwater was celebrated as a very important theme by the World Water Day. We remember the campaign, Making the Invisible Visible. And we know very well that as the impacts of climate change are getting more severe, the importance of groundwater will become even more critical, especially in the Mediterranean. That we know it's in this region, the underground water bodies are threatened by problems like pollution, salinization, especially in the coastal areas, overexploitation. And of course, this growing pressure will have severe effects on the availability of water for agriculture, for human consumption, and also for the functioning of natural ecosystems. So back in 2019, PRIMA launched a call for proposals on groundwater management, and this call resulted in the selection of these 4 projects that today organize this webinar: GOTHAM, RESERVOIR, EGROUNDWATER, and InTheMED. And the objective of the call, just to give you a bit of scope where this all started, the objective of that call was to fund research and innovation actions that could develop and validate, most importantly, some sustainable groundwater management solutions through several types of solutions, like new optimized allocation systems, monitoring and modeling tools, decision support systems, and early warning systems, and also innovative practices like, for example, groundwater recharge, aquifer recharge. And also that considered other important elements like the socioeconomic dimension of groundwater use, and also governance issues related to groundwater. So today we will learn from the projects what the work that they carried out since their launch, and of course during these challenging times, during the pandemic and the first results. There will be 2 sessions, 8 presentations in total, and during the first session we will have a chance to familiarize with the scope and the objectives of 4 projects. During the second sessions there will be thematic presentations focusing on the specific aspects of the addressed by the projects, so earth observation, data collection and sharing, role of citizen science and ICT, and groundwater governance. So well, I hope I didn't repeat too much what Damian said, because I couldn't hear him. Again, I hope it was a good introduction. I will try to fix this problem with the audio that I have, and I will close here the initial remarks. Thanks again to the projects for having me here, and for convening all of us for this interesting meeting. So now the floor goes to the coordinators for the first session. So I'm looking forward to listening to the presentation. Thanks again.
Thank you, Marco. Now, to start with, we have the GOTHAM project. Damian from Cetaqua, can you explain to us?
Okay, now my microphone is on mute. So I share my screen. Bea, can you tell me if you can see?
Yes.
Now my screen? Okay.
Yes. Thank you.
Okay, thank you, Marco. I wanted to talk about the structure of the webinar. You already did it, so that's nice. Okay, I forgot to introduce myself before. So I am Damian Sanchez. I work as a project manager in Cetaqua, and with Cetaqua we are the coordinator, the responsibles of one of the PRIMA projects. The name is the GOTHAM project. You can see in the presentation. So now for the next 10 minutes, I will present you the main works, the main thing we have done so far in the project. So you have there the complete title of the project. The main goal of the GOTHAM project is to develop a new governance tool. We call it the G tool, this new governance tool, and a governance tool for groundwater, so to improve groundwater governance. And as you will see later, it's a tool that includes numerous aspects related to groundwater. And we build this tool with the coordination of all users. So we try to follow a bottom-up approach. So we talk to the stakeholders, to water users, we collaborate with them, we agree with the things that the tool should include, and then we build this new governance tool. So of course, this is a project financed by the PRIMA call. This is a 3-year project. It started in April 2022 and it will finish the next year in 2023. So we are now in the final stage of the project. So the project has 7 partners. 3 of them are from the European Union, Spain, France, and Italy, and 2 associated countries, in this case, Jordan and Lebanon. We have 3 use cases, 3 pilot sites. The main one is located in Spain. Here you can see in the left side is the Campo de Darías groundwater body. You can see on the picture on the left side, the white color corresponds to greenhouses. So you can see as there is a huge area of extension of greenhouses, which are fitted with groundwater. So you can imagine the problem we have there. And the 2 other replication sites are located in Yahat in Lebanon and in the Azraq Basin in Jordan. So this is the structure, the architecture of our tool, the tool we are developing. You can see we have 5 main columns, 5 main elements. We have data sources, so the data we use to develop the models included in the G tool. So we have data layer where we manage this data. And then we have the analytics layer. This is like the heart, the engine of the tool where all the analyses are carried out. Then we have the service layer, and the service layer you can imagine like the platform you are going to see, the user is going to see, the platform where all the models will be implemented. And finally, we have the users, the beneficiaries, and we will create different profiles depending on the user. So a different profile for each different user. So now in this presentation, I'm going to focus on these 2, on the 3 last elements of the G tool. So these are the models, the capabilities we have included in our G tool, in our governance tool. So we have included a groundwater recharge recommended system. We have included 3 different methodologies to calculate groundwater recharge. So the tool will be able to carry out these analyses, and the user will get the final data the user will get will be the total groundwater recharge. So you have here an example from using the Uplifts method for carbonate aquifers. We also, the G tool also have this groundwater potential mapping. So on the right side, you can see the final map, and we calculate the potential to find groundwater depending on some characteristics like land use, slope, geomorphology, geology, of course, drainage density. So depending on these factors, we calculate the potential to find groundwater in your study area, from very low to very high. We have also implemented a hydrogeological multivariate analysis. In this model, we have included 6-7 different hydrochemical and statistical charts, from the very well-known Piper diagram, of course, to principal component analysis. And we have also implemented the assessment of trends for hydrochemical parameters, so that we can forecast if one specific parameter, for example, nitrate or electrical conductivity, will be under or on the maximum limit. So as I say, 6-7 different analyses in this model. We have also done the forecasting of surface water reservoir and groundwater levels. So you can see in these two charts on the left side, you have the black line. You see the historical water level in the reservoir, and on the right side, these three lines in green, blue, and red are the forecasting values. We did it here in 2021 for 2022, depending on the how to say, the pluviometric year. If we have a normal year, a dry year, or a humid year, so we do this forecasting, and the same for groundwater level. So we have the historical data set on the left side, and on the right side we can do the forecasting. So to foresee the groundwater and the reservoir water level in our study case. We have also included an assessment of the SPI index. So we calculate the SPI index, and we also do a forecasting for the SPI index, so we can foresee if we will be in a dry situation, a humid situation, in a normal situation. And we also calculated a scarcity index. So this scarcity index is the combination of the two previous values. So we can calculate the forecasting value for the surface water reservoir. We can also calculate it for groundwater. So we combine both of them. We can know if in our case study we will have how to say, a good a normal quantity of water stored in our aquifer surface water reservoir, or we will for example, if your point is in the green area, it means that you have a normal situation. If you are in the red area, it means that you have a dry situation. We also included the estimation of land use changes. So we have developed an automatic tool to classify land uses. So current land uses, so we can automatically done this using remote sensing, using data from satellites, and we can also estimate the prediction of land use changes. In this case, we have done a prediction for 2025. And why is this important? So what is the link between this and groundwater? Well, so this is important because some land uses are directly related to groundwater consumption. It means that, for example, if we have an increase in the area of greenhouses, it will mean that there will also be an increase in groundwater pumping. We have also included in our tool an estimation and assessment of the potential to carry out managed aquifer recharge facilities. So if this is the final map and you have different colors. So in the green color, you have areas where you have a high potential to carry out managed aquifer recharge activities. In this case, ASR recharge, and you have the red areas where the potential, you have a low potential. So these are not areas suitable to do managed aquifer recharge. So we did it for two different methods, for ASR recharge and also for infiltration ponds. So we have these two maps. Also, we have this aquifer remediation tool. You can see here. The user will be able to choose a contaminant out of a selection of 7-8 different contaminants. Then he will be able to choose a remediation method, different remediation methods, depending on the contaminant. And then the user will have a summary of an estimation, if you want, of the CAPEX related to this specific remediation method, and OPEX estimation also, the expected reduction of this contaminant, advantages, potential problems, and some technical consideration for the calculation. So This is like a first step in case the user is thinking of applying some remediation techniques. So he will be able to have a first, if you want, a general characterization of the different remediation methods. And this is the final module of our GTOL. We call it the Groundwater Bodies Response Module. And so the objective of this module is to foresee the groundwater status, the status of our groundwater body, considering the previous models. So we take into account groundwater quality trends, the scarcity index and drought index, the potential to use non-conventional water resources, regenerative water, the potential to carry out managed aquifer recharge, the aquifer remediation tool, and also the groundwater governance assessment. I didn't show you, but we have also, so you will see at the end of the last thematic session a methodology to assess groundwater governance. So we put together all these variables and we do a forecasting of the most probable status of our groundwater body in the, for example, in 1 year, in 2 years. So this is the final result of our GTOL. Just so this is like the GTOL looks like currently. So we are still developing some, we are still implementing some model, but this is what the user will see. So he will go on the internet, he will get into the platform, and he will see a list of the different submodels. He will click on the specific submodel. In this case, I selected the drought monitoring and the scarcity indexes, and he will see this. So the historical index, the historical data sets of the index, and the prediction considering wet year, medium year, or dry year. So just to finish, as I told you, we are developing this GTOL in collaboration with stakeholders and water users. And for this reason, we are carrying out workshops with these stakeholders. We have already done two workshops. The last one was in last May. We have still one left that we will organize in January, next January. And as you can see during these workshops, we present the different models, the different tools we have developing. We get their opinion, what they are interested in, what they are not interested in, and we adapt our GTOL to their opinion. So this, for us, this is a very important element of our project. So you have here some pictures. As you can see, we created some, we developed some working tables with a stakeholder from the same category, for example, farmers or groundwater managers, for example, and we got their opinion. And that's it. So here you have the social network of the project if you are interested in. And of course, if you have any question, you can write your question in the chat, or later we will open microphones if you want to ask something regarding this project. So thank you.
Thank you, Damian. Now we are going to explain the project, and Claudia Medicina from the University of Pavia from Italy is going to explain it.
Thank you, Beatrice.
Thank you.
And good morning, everybody. I'm Claudia Medicina. I'm from University of Pavia, and I'm the coordinator of the project RESERVOIR. That means sustainable groundwater resource management by integrating earth observation-derived monitoring and flow modeling results. Then the project started in March 2020 and has a duration of 38 months. Then we are about in the middle of the project. And the consortium has a multidisciplinary expertise and come from 4 countries in the Mediterranean area. In Italy, we have the University of Pavia, who coordinate the project, the Consorzio di Bonifica del Canale Emiliano-Romagnolo, and the University of Padova. In Spain, there is the Spanish Geological Survey and the University of Alicante. In Turkey, the Dokutsayl University and the University of Jordan and the Azraq Wetland Reserve for Jordan. We have also in the consortium some end user as the Azraq Reserve and the Consorzio di Bonifica that are involved as partner in the project. Then, which is the problem that the reservoir project want to solve, and which is the approach of the project? We know that aquifer systems are a main resource of fresh water in the Mediterranean areas, and this results in aquifer overexploitation. One of the effects of the aquifer overexploitation is the lowering of the land elevation. It means the land subsidence that can be measured from the space through earth observation techniques. And these techniques allow us to investigate large areas. They are non-invasive and they are also low cost. For example, the Sentinel-1 mission, as part of the Copernicus program, adopted a free and open data policy. And then in this project, we adopted the data of Sentinel-1 mission. This is the starting point of the reservoir project, in which we use the land subsidence measure from space to study the properties of the aquifer. Because another very important challenge is the fact that the groundwater systems are often very poorly characterized due to the lack of good quantity in situ data, like groundwater level, aquifer storage, pumping rates, and it is a very critical drawback for the sustainable groundwater management. Then the reservoir project will help to fill this gap because the objective of the project are to developing an innovative methodology for the hydrogeological characterization of large-scale aquifer system using advanced satellite SAR interferometry, and then integrate this data into numerical groundwater flow and geomechanical models in order to help the sustainable groundwater management. We have 4 pilot sites that correspond to 4 water-stressed areas in the Mediterranean that correspond to different typologies of aquifer. In all this area, the agriculture is the main economic activity. In Spain, we have the Upper Valentin Basin, and there is a detrital sedimentary aquifer, and here the reservoir project will give a contribute in understanding how we can manage groundwater resources to avoid the groundwater overexploitation and subsidence risk, because this area was recorded the highest subsidence rate in Europe due to groundwater extraction. In Italy, we have the Comacchio coastal aquifer, in which we have an alluvial aquifer belonging to the Po River plain, and here the question is how to analyze the relationship between saline intrusion and also the land subsidence, and to understand the effects of water leakage from the irrigation network in order to avoid salinization. In Turkey, we have the Gediz River Basin. That is one of the most stressed basin in the country, and here the reservoir project will give a contribute in the understanding of how to manage groundwater resources to ensure a sustainable use of groundwater. And then finally, we have as a pilot site the Azraq Basin in Jordan. That is a very complex aquifer system, which we will give a contribution in the understanding how we can manage groundwater resources to preserve the groundwater dependent ecosystem, because in the Azraq Basin we have the Azraq Wetland Reserve. It is very important from the international point of view, but it is degraded in the last year due to the groundwater overexploitation. The reservoir products concern the land subsidence mapping, the aquifer system characterization, the future scenarios of aquifer exploitation, the best practices for decision making, and until now we have reached 3 milestones. First of all, we develop a methodology for the end user requirements. Second, we map the land subsidence in the pilot site, and then further we characterize the aquifer system in this pilot site. As far concerning the end user requirements, the end user are different in the different pilot sites, but they generally belong to national and local authorities responsible for water land use management or to governmental organizations at the municipal, regional and country levels. They were interviewed through workshop, webinars and questionnaires, and the analysis of stakeholder requirements is given insight about the different issues that exist in the pilot areas concerning the groundwater management. For all the end user, the main problem in the pilot site is the overexploitation of groundwater, but they have a different perception of the land subsidence. Then for some of them are aware of these problems. Then all the end user agree that there is a lack of a good monitoring network, and there is the necessity to develop a long-term monitoring activity to generate knowledge about the groundwater status, to define benchmarks for evaluate the adequacy of the monitoring network concerning groundwater, considering the frequency of data acquisition, but also the spatial distribution. And the end user are also aware that numerical modeling can be an effective tool for the groundwater management. Then there is the necessity to develop a periodic updating of groundwater flow model as supporting the management groundwater tool. To formulate appropriate management scenarios considering the transient state of the aquifer. Then second milestone that we reach, but I will very quick about this because is the topic of the thematic session. We produce a ground deformation map of the pilot site. For the coastal aquifer of Comacchio, we don't detect any clear displacement from space using Sentinel-1 data in the period January 2016 and May 2019, and this means that there is a decrease of the land subsidence which was detected in the past. For the Alto Valentin aquifer, the ADINSAR analysis confirmed the presence of a subsidence in the northern part of the basin in the order of 7 centimeters per year. In the Geddes River Basin, we identify new subsidence in the eastern part with a velocity up to 19 centimeters per year, and in the Azraq Basin, we identify subsidence but also uplift movement. Then we will use in our project this data, this remote sensing data into groundwater modeling. This is the main challenge and main novelty of the project. But it is necessary to understand if these subsidence, if these ground movement are related to groundwater extraction or are related to water processes. Then we analyze for each pilot site the different driving and conditioning factors of land subsidence that are namely soil compressibility, the variation of the effective stressed state, and the thickness of potentially deformable layer. For all the pilot sites, there is a clear relationship between soil compressibility and land subsidence. As far concerning the variation of the effective stress state, except for the Comacchio area in which we have no subsidence, generally we have a good relationship with the water well density, the pumping volume in some cases as in the Alto Valentin Basin. And as far concerning the thickness of the soft soil, only for 2 of the pilot site, we identify a clearer relationship between the distribution of unconsolidated soft soils and the displacement. Then it means that probably in the other 2 pilot sites, as the Azrak and in Comacchio, there are also other processes which give rise to the subsidence. Then the deformation detected through the satellite were related with the piezometric data in order to construct stress strength curves and to obtain some information about the deformation behavior of aquifers. Unfortunately, we have a lack of good quality of data, especially piezometric data in the pilot site, but we identified the existence of elastoplastic behavior in the Comacchio, Geditz, and Anzark site, and a plastic behavior for the Valentin basin. We also identify a delays for the seasonal component of piezometric as in this displacement, probably related to the poor drainage related to the fine-grained layers which constitute the aquitard. Which is the ongoing work now? We are developing a numerical 3D transient groundwater flow model in all the pilot sites. This flow model will simulate time variable hydraulic head responses to different groundwater pumping scenarios, and this model will be used in conjunction with the subsidence model, the geomechanical models. The next step will be to the simulation of the results of the earth observation techniques into the numerical ground flow model and the subsidence model in order to characterize the storage of an aquifer system that can help in the sustainable groundwater management. Then these are all the contact of the reservoir project. Then if you have some questions about the reservoir project, you can write in the chat. Or otherwise, here you can have more information. Thank you very much for your attention.
Thank you very much, Claudia. Now it's time to groundwater project, but I think Manuel Pulido is having technical problems. Can you hear us, Manuel? Your microphone is off.
Yeah. Yeah, you have to unmute your microphone. Yeah.
No, we can't hear.
Not yet.
Okay, so if you want, Jaime, if you are here, we can change the project and you can explain InTheMED. Are you here?
Yes, I'm here.
Okay, if you haven't got any problem, if you can explain your project InTheMED.
Well, apparently I do have problems to share my screen.
If you can't share your screen, you can send to me the presentation and I can share the screen for you.
Just a second. Okay, while I try to fix it, I'll send you my presentation, just in case.
Okay, thank you, Jaime.
Manuel has joined again. Can you hear us?
Yes, I can hear you. Can you hear me?
Yes.
Okay, wonderful.
Very well.
Do you want me to proceed with the presentation, or was Jaime doing that?
Go ahead, because I also was having some problems with it.
Okay, thank you, Jaime, as well.
I'm
Okay,
really
so now it's time to eat groundwater by Manuel Pulido from the Universitat Politécnica de Valencia. Go ahead, Manuel, thank you.
Okay, so just let me check that I can share the screen.
Okay. If not, I have your presentation, so don't worry.
Okay. So just a second. Okay, so I'm trying to share. Okay, so yeah. So it's possible that you see my screen now?
Not yet.
No, at the moment. Nope.
Okay. So I'm not sharing yet, no?
Nope.
No.
Okay. So let me. Okay. Now I see. So second screen. Sharing. Maybe now?
I cannot see your screen now.
No?
If you want, I can share my screen with your presentation.
Let's try. If not, we can.
Okay.
So now?
No.
No, it doesn't work. Okay, so please, if you can share the screen, and then I will tell you when to pass the slides.
Okay.
Yes, please.
I can see your screen there now. Yeah.
Okay, perfect. So go ahead and tell me when I move on.
Okay. Thank you very much. First, apologize for these technical problems. Basically, well, I'm going to make a quick summary of our PRIMA project, EGROUNDWATER. So EGROUNDWATER started in March 2020. It's a 4-year project, so we passed the middle of the project, and we have partners from Europe. So we have partners from Spain. So we have UPV, we are coordinating the project. We also have eCatalyst, a consulting firm based in Madrid. We have also from France, BRGN, the Geological Survey of France, and also CIRAT in RAE. And from Portugal, we have 2 partners. One is from the Lisbon School of Economics and Management, and the other one is from the Universidad of Algarve. And finally, we have Visual Naphtha, is another consulting firm working in the development of the mobile app that I will present. And then 2 partners from Africa. One is from Morocco, University of Medmex, and the other one is from Algeria, University of Adrar. Can we go to the next slide? So our project is about citizen science and ICT-based enhanced information system for groundwater management. So we know that, we all know here that we have this challenge. Data is always a challenge for groundwater management. So data availability is often an obstacle for an efficient groundwater management, and groundwater information is crucial also for participatory processes in groundwater management. But we also know that traditional information systems have limitations. Also, they are costly to maintain and further develop. And the other limitation is that we have a limited spatial and time coverage. So in this project, we are looking for alternative ways of increasing groundwater information in order to support a more efficient and sustainable groundwater management. So the solution proposed by eGroundwater is the design and use of innovative information systems and combined with models and participatory strategies for groundwater management. So can we please go to the next one? Well, so this is a summary of the method that we are implementing in this project. So basically, we have the collection phase, data collection, collection of data and information, and the novelty here is that we are going to combine traditional information system in which we are including weather station, piezometers, stream flow gauges, with citizen science involving the users. So the users are going to be engaged in collecting measurements of groundwater levels, pumping rates, water use, and water quality. And this is going to be done through a web platform and a smartphone application, what we call the app in the project, and that is in the process of development right now. We are also combining this with Earth observations. So we are using Copernicus services for meteorological variables, and we are combining satellite and drone images to estimate important variables such as crop evapotranspiration, irrigation water needs, or, for example, vegetation dynamics. So we are combining all this information, also including sensors for measuring soil moisture, pumping rate, etc. And the idea is to improve our data and information on our groundwater cases, and to use all this additional information to improve our characterization of the aquifers, and to use groundwater models and participatory process to improve groundwater management strategies. So can we go to the next one? So this is a formulation of the specific objective. So evaluate information system and combine with ICT-based tools to improve and enhance the information. To combine this with groundwater assessment and modeling and improve groundwater management strategies, and then to assess what are the socioeconomic impacts of enhanced groundwater data availability, capacity building and institutional transition, and finally to do a scaling of the results for PRIMA countries. So next one, please. Okay, so we have in Groundwater project, we have 4 case studies. One is Requena Utiel in Spain. Is a case study that we are sharing with the next project to be presented in the MED. We have also a case study in Portugal, Campina da Faro, and 2 cases in Africa, one in Morocco and one in Algeria, what is an oasis. Can we go to the next one, please? Okay, in the project, we have a work package that is basically devoted to develop the framework for the project on how to define and incorporate citizen science and information system in groundwater management. So the first thing we are doing in this work package is to develop the literature and to develop successful cases of including innovative information system for groundwater. So can we go to the next one, please? So as part of this work package, we have done a literature review, and we have developed what we call a card deck of concept, definition, and examples of citizen science in groundwater. So can we please go to the next one? So this is the card desk. This has been led by Catalyst, by Elena Lopez-Gun and her team, and is providing training material for the definition of citizen science and enhanced information system in the case of groundwater. So we are producing a package of cards that are going to be used with the stakeholders in the training sessions in order to discuss and improve the knowledge on what citizen science is. Can we go to the next one? So these are the topics that are presented in this box of cards about citizen science, about collective action, about key groundwater issues and data management, and also about the use of new information technologies and satellites. And then a collection or an explanation of the case studies we have in our projects. Can we go to the next one, please? Just one example, and also what are the motivation to participate in citizen science? So we describe the different motifs that are enhancing the stakeholder participation in data collection. So next one, please. All the types of citizen science and how to translate this into groundwater participation. Next. And collective action for groundwater management. So we collected examples from different countries. What we're completing now with the reference cases that I'm going to show. So can we go to the next one, please? We have conducted also a Delphi study on main trends on groundwater policy in relation to data information and knowledge for decision-making and collective action. So a Delphi study is a type of participatory foresight study in which we conducted, it was a large survey with experts on groundwater management. Probably some of the people who are attending the seminar participated in this survey. And collecting opinion from experts on feedbacks on how to use information to assist decision making in groundwater management. So next, please. So we move to the next one. The result of these surveys are available as a deliverable of the project, and I think it's a very nice overview of what's expert feedback on this type of study. Next one, please. For example, what do experts say about enhanced information system and citizen science? This is very relevant because the understanding of enhanced information system is different, and we see different point of view regarding this issue. So can we go to the next one, please? Next.
Sorry, we need to run a little bit.
Okay. Just reference cases. We are just selecting what we call micro cases or successful cases of citizen science. If we go to the next slide, you can see a map in which, next one please, in which we present all the cases we are studying in the world about successful use of an innovative information system for improved groundwater information and data. So all these, we are studying all these cases. Next one, please. So this is put in the framework. We have a work package devoted to stakeholder engagement and development of local focus groups. This has been done for the 4 cases. Can we go to the next, please? So it has been done for Morocco, for Algeria, just some pictures of the participatory processes with the stakeholders in order to define how to improve knowledge and data in groundwater use and groundwater management. Next. Next one, please. So this next one. So this participatory process has been crucial for the development of the web and the mobile app for the project. If we go to the next slide, you can see some pictures of the tool we are developing together with the stakeholders. It's a co-design process. In the next one, please. Next. So this is some examples. We are developing a tool that the users are going to use. It's very user-friendly, in which they are going to introduce data on their own irrigation fields, their own pumping wells, water levels. In some cases, they introduce also water quality and water use. Can we go to the next one? It's a two-direction information. So we are sharing information on efficient water use, and they are sharing information on their own irrigation field and pumping conditions. Can we go to the next one? This is the information we are providing to the farmers. We are providing information on crop water requirements and irrigation water needs, on crop water use, estimation using a combination of remote sensing and agronomic models, and also providing advice to the farmers on efficient irrigation, combining this with forecasting tools. I will present this in the afternoon session of this webinar, so I will present more in detail what is the approach that we are following for this assessment. Can we move to the next, please? Next one, I will explain this in the afternoon, as I said. Next one. Next, please. Next. So all this is now being implemented in groundwater management models, in which we are assessing what is the added value of the additional information we are collecting and the participatory process for the development of more efficient groundwater management strategies. Next one, please. And this is under discussion with the stakeholder of the 4 different cases we are having in the project. Next one, please. Next, please. Finally, as part of the project, we are also doing capacity building, so training programs in the different countries, in Portugal, including schools, in Morocco, building and using locally made probe to measure water levels, groundwater levels, and also involving local policymaker and water management through workshops and international meetings. Can we move to the next? Just to finish, we are going to have a meeting in October in Valencia involving the key decision policymakers and stakeholders from Morocco, Algeria, Tunisia, France, and Portugal, coming to Valencia to share experience and have a field trip and visit different cases in which we have innovative groundwater information system. Next, please. You can go to the project web page and find videos and more information on the different meetings and participatory processes, and also to the Twitter account that was shown at the beginning of the presentation. Next. And that's all. Thank you. Thank you very much.
Thank you very much, Manuel. And to finalize this part, we have InTheMED and Jaime Gómez Hernández from the Universitat Politécnica de Valencia. Please go ahead, and please, we have no more time, so please run.
Okay, are you seeing my screen?
Yes.
Good.
Thank you.
Okay, so I will present very briefly the InTheMED project in this second webinar on groundwater, a common challenge. The title of the project is Innovative and Sustainable Groundwater Management in the Mediterranean, and our objective is at the end to have a decision support system that can be used both by the water authorities as well as by the users in order to query the aquifers, to query the system. So what's going to happen under several circumstances, like related with climate change, increase of irrigation demands, increase of pumpings, or change of land uses in the aquifers. We have 5 pilot sites. We have 7 partners, 5 pilot sites, one in Spain, one in Portugal, one in Tunisia, one in Greece, and one in Turkey. And then we have 2 partners, Germany and Italy, that do not have case studies on their territories. And the project is built on these 4 pillars that you see here. We're trying to do some kind of innovative groundwater management, in which first we want to have as much information as possible about the history of what has happened in the aquifers, and use those to find out trends and to try to understand, which is the situation on those aquifers. Then we want to improve the resilience of groundwater in the future, and try to make it, as I said, as most resilient as possible to the different impacts that the aquifers may have. We want to develop some kind of sustainable management, remediation, and management strategies that are basically the core of this decision support system that is going to be built in relationship with the stakeholder, with communication with them, and with important dissemination activities. A very important part of the project is that all these pillars are based on a participatory approach in which the stakeholders have been engaged from the very beginning in these case studies. I'm not going to enter into the details of the 5 case studies, just some numbers for you to see that the size of the aquifers go from very small to very large, that some of them are inland, some of them are coastal, some of them have problems of contamination, basically of nitrate and seawater intrusion, and only one of them doesn't have that problem. Most of them are overexploited by one. So we are tackling, I mean, very common situations in the Mediterranean area regarding the situation of our aquifers, both from a quantitative and from a qualitative point of view. The work packages of the program of the project are listed here. The most important ones are the monitoring and data analysis package 2, the smart modeling package 3, the governance and socioeconomic assessment package 4, remediation strategies in package 5, decision support system in package 6, and of course the dissemination and communication that has to be through through the entire project, and in which this seminar is part of this package. The partners on the project are the Universitat Politécnica de Valencia. I'm the coordinator here in Valencia, the Technical University of Crete in Greece, the Helmholtz Center for Environmental Research in Germany, the University of Parma in Italy, the Association for Investigation and Research from Portugal, Water Research and Technologies from Tunisia, and Boğaziçi University from Turkey. And I'm going to show, well, and this is just basically a cartoon summarizing the different work packages, how they are related among them. I mean, how we want to involve all the stakeholders, non-governmental offices, authorities, and at the end, basically, we want to get this sustainable groundwater use and protection, not forgetting the climate change, which is hovering at all moments in our analysis. And now, very quickly, I want to show you just some snapshots of what we have obtained so far. Regarding data collection and sharing, that will be the topic of the thematic session that it will come later. We have done a very important effort on collecting information about groundwater levels around the Mediterranean, and we have collected close to 12,000 time series, and we have analyzed them, and you will hear about that when Saif makes the presentation later today. Regarding smart modeling, we have developed these smart models for the different case studies, and these smart models will be part of, they will be input into the decision support models so that they can actually do whatever optimization, whatever analysis in a very fast fashion. This is an example from the Requena-Utiel Aquifer, in which we have trained a neural network using basically running a Mothflow code on the whole aquifer for for many years, and with many different situations about different variations in the recharge or on the amount of pumping in the aquifer. And we have predicted the piezometric heads at a selected number of piezometric sampling points. And with that, we have trained a random forest-based surrogate model that in a matter of milliseconds will be able to give you the behavior, the response of the aquifer to whatever is the changes in recharge or changes in pumping that you may want to ask in the future with a span of 50 years from now. Regarding stakeholder involvement, we have certainly had, we have, in this case, we have been collaborating very closely with the EGROUNDWATER project. We have the same case study here in Spain, and we have met wineries, city halls, farmers. We have conducted living labs with them that have served to build this socioeconomic model that also is an important part of this, is the decision support model that will be the final product of the project. Regarding remediation strategies, we have analyzed each case study, trying to identify which are the problems that occur in that specific case study. Here is just showing you the case of Groundwater in Tunisia, in which well, there are two items identified, both in the industrial sector and in the agricultural sectors, with the problems that have been identified and who would be the target groups to contact, just to try to find a solution that in which is co-created with the stakeholders as well. And finally, regarding the decision support system, I mean, everything that that comes from the previous packages at the end coalesces in this final package, in the decision support system, in which the smart modeling will basically allow you to make very fast runs. I mean, the data collected will allow you to have a better understanding of what the situation is. I'm showing here just two images of the Tompaki aquifer in Greece, both in the dry season and in the wet season, in which an optimization has been carried out to find out which would be the maximum amount of water that can be extracted from the aquifer, preventing that the aquifer goes below 6.5 meters at some distance from the coast. The coast is on the left. The line that you see there with the flags correspond to these points where we want to make sure that the groundwater doesn't go below 6.5 meters, just to prevent seawater intrusion into the aquifer. The results are in the table that I'm not going to discuss, but the main conclusion is that using this decision support system and this optimization approach, you can basically be able to get 1 million of cubic meters a day in addition to what is actually being extracted from the aquifer, and still maintaining this restriction of the 6.5 meters. And that's all what I wanted to say about InTheMED. Thanks very much.
Thank you very much. Now we are going to continue with the thematic sessions. Roberto Tomás from the University of Alicante will talk about Earth observation for improving groundwater characterization. So please. Your microphone is off. We can't hear you. Can you hear us?
Yeah, your mic is muted.
Yes.
Yeah, we cannot hear you. Not yet, Roberto.
Okay, now can you hear me now?
Okay.
Oh, sorry.
Thank you.
Okay. So can you see my screen?
Yes.
Okay, so first of all, as you know, my colleagues from the Geological Survey of Spain, they unfortunately couldn't attend the meeting. And then they have a record, a video that I'm going to show you, okay? So first of all, I will show you the video from the Geological Survey, from the IGME. Oh, sorry, wait.
If she's talking, we can hear her.
Yeah. We cannot hear anything now.
When you share your screen, you have to put a button to
So
share.
you cannot hear the video?
No.
Okay.
No, we can see it, but we cannot hear.
When you share your screen, there is a button to put the sound from the PC.
From the video, but
Yes.
okay. I will do it again.
You share your screen?
Ah, yeah, I see.
Yes.
Okay. Let's try again.
In this
Okay.
video,
Fine
I
now?
will explain
Yes,
the results
perfect.
of the terrain deformations at our 4 pilot sites, which were analyzed with the InSAR technique. As you all know, the groundwater depletion can cause land subsidence, which can be detected and monitored by 8 INSAR techniques. Assessing land subsidence is key to understand overexploited compressible aquifers and to be able to perform coupled modeling of aquifer deformation and groundwater flow. In this project, we've used SAR data from the Sentinel-1 satellite, which is part of the Copernicus program of the European Space Agency that has a free and open policy data. Sentinel-1 is a constellation of 2 satellites with a revisiting time of 6 days. The radar sensor operates at C-band, and the images have a width of 250 kilometers. The spatial resolution is 5 meters in azimuth, which is the north-south flight direction of the satellite, and 20 meters in range, which is the perpendicular direction of the flight track. We performed 2 types of analysis. The first one was a preliminary process with the aim of identifying potential terrain movements in the test sites, and the second one was a more refined and conclusive analysis focused on the more relevant deformation areas. The preliminary analysis was done in the GeoHazard web platform, which is a service where both SAR images and processing chains are available in one single interface. The processing here is unsupervised, which means there is very little user interaction, and only a few parameters can be tuned. We use 2 different algorithms of this service, the PS-bus and the FastBell, but in this presentation, I will only show the PS-bus because the FastBell results were very noisy. The final processing was performed with the Cpt software. In this case, all the processing chain was supervised and the parameters were carefully chosen. From this analysis, we obtained mean loss velocity maps and time series of displacements in the line of sight of the satellite. Let's explore one by one the terrain deformation results of the 4 water-stressed Mediterranean aquifers. We will start with the Comacchio coastal aquifer in Italy. Here we have the preliminary results obtained with PS-bus. We processed separately Sentinel-1 images acquired in ascending and in descending orbits. Each dot of the map is a measuring point that indicates the velocity in the line of sight of the satellite. So red color indicates movement away from the satellite, blue color indicates movement towards the satellite, and white means no movement. In Comacchio, we haven't detected any terrain movement that could be directly related to land subsidence, which does not mean that there could be a very low regional deformation rate below our stable threshold that we established in 1 centimeter per year. These are the results obtained with the Cpt software. Again, only very local movements were detected that could not be related with land subsidence. This was a very difficult area to process, firstly because it is intensely cultivated, which means there is a loss of temporal coherence, so the point's density is very low, as you can see. And secondly, the crop's growing cycle and changes in humidity were introducing noise in summer, so the summer images were discarded, as you can see in the time series. We now move to Alto Valentin aquifer in South Spain. At the left, the preliminary results obtained with PS-bus. We see the maps of ground movement velocity on the line of sight of the satellite in ascending and descending orbits. On the left, the results with the Cpt software in descending orbit. Please note that the period studied is different. There is a clear deformation pattern visible in all the processings in the northwestern part of the aquifer. Here we see the displacement time series of the points at the maximum velocity areas, and we can see that the pattern is very linear. Now we go to Turkey. Here we see a picture of the deformation at the entire Gediz River basin, thanks to the capacity of PS-bus to process really big areas. we can notice several deformation spots that have different time series trends. Ones are more linear and other ones have a seasonal pattern. Again, the information gaps, it's because the C-band is not capable of detecting measuring points in vegetated areas or with dense crops, but we do have high density in the stable mountains surrounding the valley. For the Cpt processing, we focused only on the most eastern part of the basin. At the left, you can see the PSPAS results, and in the right, the Cpt results. First thing we notice in the Cpt processing is a dramatic improvement of pixel density, which is because the quality threshold for selecting measuring points was lowered. This means some points, we know which ones, are less reliable, but in contrast, we are able to see in a qualitative way that the deformation extends through the agricultural land cover. The time series also vary depending on the zone, and here we have an example of these high deformation areas where we can see a seasonal trend. To finish, the Azraq Wetland Reserve in Jordan. Here the point density is really high except for the flooding area of the wetland. This bare soil is very suitable for the INSAR processing with C-band. Something interesting was the detection of uplifts. You can see them in blue. We are still studying the origin of these uplifts. Among other possibilities, they could be due to shrinking and swelling of clays. The time series trends also differ depending on the zone. Here we see an example of points located at the red circles. Again, notice that the time period overlap, and we can see some kind of seasonality. Thank you very much for your attention. I'm sorry for not being able to attend the webinar. If you have any doubt or question, please contact me. Have a nice day.
Okay, so this is the presentation from my colleagues from the IMED. So if you have any question, I can also try to answer the question during the 5 minutes for discussions. Okay, so now I'm going to present. I don't know if you can see. Yes, you can see my screen.
Yes.
Okay, so I'm going to show you the results from work package 4. It's a work package from that has already been finished in the reservoir project, and it's a work package. Sorry.
No, I think there is someone with a mic on.
Let's continue.
Okay.
Thank you.
Okay. So this work package is the aim of this work package is to analyze all the results from the study area in order to validate and interpret the Earth observation dataset. This is the main aim of the work package. So the methodology that we have followed in this work package was first consisted in the compilation of information from the 4 pilot sites. So we obtained information, for example, from geological maps, boreholes, time series of piezometers, also Earth observation information that was developed in the previous work package that has been presented in the video. And also we also compiled information from in situ monitoring systems, GNSS stations, leveling, extensometers, and so on. So all this information was integrated into a GIS system. So we created a very big database of all the information from the 4 pilot sites of the project. And then with this information, the first step was to validate the information, the in situ, the Earth observation data. So we compare the in situ data, the INSAR data with in situ data in order to evaluate the quality of the information. So we obtained some reports. We perform a spatial and temporal analysis in order to obtain the metrics of the comparison. So once we know that the information, the Earth observation data are good, then we move to the next step. The next step was the use of the time series obtained by INSAR, by Earth observation techniques, in order to be compared with water levels. So we compare both time series, and then we obtain the stress strain curves. These type of curves relate the deformations of the ground surface with the changes in the bathymetric levels. So these curves provide us information about the deformational behavior, the response of the aquifer against water level changes. So these curves allow us to classify the aquifer system into different types of deformational behaviors: elastic, elastoplastic, plastic. So we can classify according to the deformational behavior all the aquifers from the 4 pilot sites. Next step was to analyze all the information that we integrated in the GIS platform in order to obtain correlations, to find relationships between land subsidence and also conditioning and triggering factors of land subsidence. So we analyze, we perform all the type of analysis in order to find these relationships and correlations. This information, the results, obviously allowed us to characterize and interpret the phenomena affecting each of the 4 pilot sites. So let's see now the samples very briefly, obviously, because we have a limited time, the results of some of the study areas. So, okay, for Comacchio, the first study area is on the northeast of Italy. Here you can see the INSAT results that have been presented, also introduced by Claudia and by Guadalupe in the video. So the first task was to validate the results. So in this case, we compare the INSAT time series with the INSAT time series in the red line, sorry, with the continuous GPS time series. In this case, you can see that the results were quite good. So there was, we can say that the correspondence, there were a good agreement between both time series. So once the time series of INSAT have been validated, next step is to analyze this time series jointly with piezometric levels. In this case, there were piezometers, shallow piezometers and deep piezometers. Here you can see the distribution of the piezometers and the time series. And then comparing, for example, this is one of the piezometers, comparing the piezometer time series with the evolution of the deformations that is represented by the dashed lines, we can obtain the stress strain curves. In this case, due to the sampling frequency of the piezometers and other issues, so the relationship is not very clear, but it seems, or at least we recognize some elastic behaviors, mainly in the shallow aquifer of Comacchio. We also analyze, for example, we compare the deformation, the INSAT displacements, with the subsoil thickness distribution obtained from Cpt, from boreholes in the study area, and also the relationship between land subsidence and water level changes. The relationships were not good enough, so they didn't clearly show a relationship between subsidence and this conditioning and triggering factors. Yes?
2 minutes, please.
Okay, so in the Alto Valentin aquifer, we also performed the validation. The results were very good. There was a very good matching between both time series. And the stress strain curves, these are the piezometric time series, the distribution of the piezometers, and this is the evolution of the subsidence against the piezometric level. And you can see there is not a clear relationship. There is a continuous, a very linear, and a very fast deformation. So in this case, we can state that the behavior of the aquifer was mainly plastic. So there was an inelastic deformation. In Valentin, we also found a relationship, a very clear relationship between the subsoil thickness distribution and the deformation, the INSAT deformations. For example, we performed 2 cross sections. Here we can see the subsidence, and this is the subsoil thickness. So the thicker the subsoil thickness, the higher the subsidence. It's a clear relationship as expected. In Gedit River Basin, we also validated the GNSS data, the Earth observation data with GNSS time series. Both time series correlates very well, so the metrics was quite good. And we obtained also the stress strain curves that in this case, there were problems with the piezometers because we had very few piezometers. Also, the sampling was very long. The frequency of sampling was not very good. And there was a connection between different layers of the aquifer. So, but in this case, we recognize some seasonal changes and a general trend. So we can state that in this area, the deformation that we are measuring in the aquifer are mainly elastoplastic. So here we also found a relationship between the subsoil thickness and the displacements, okay, like in Valentin, and also identified some structural control of subsidence by faults. This is the Sarigold fault that we visited during a meeting of the reservoir project a few months ago. And here we performed some cross sections, and here we represent the cross section. So you can see at both sides of the fault, the deformation is different. So here is the foot wall exhibits a quite stable behavior, but in the hanging wall, as you can see here, there are some deformations. Here you can see the fault, okay, in situ, and also some cracks caused by the fault in the area of Sarigold. Finally, we studied the Afterlife wetland in Jordan. In this case, as it was previously mentioned, we process it with PSBus and CPT. We have not, in this case, in situ data to validate the information, and then we perform a cross-validation between both processings. That, unfortunately, didn't provide very good results. Here, we also had an important lack of information, piezometric information, but in two piezometers, we compared the piezometric evolution with the deformations, and we observed also a seasonal variation of the deformations with a general deformation trend. So we can state more or less that that this area presents an elastoplastic behavior. We also compared the distribution of wells. So we perform a kernel analysis in order to evaluate the density of well, the relationship between the density of wells and the subsidence. And we found that in those areas in which the density of wells was higher, the subsidence was also higher than in the other areas. So there was a certain relationship between the location of the wells and the subsidence. So at the end, as a summary, as a conclusion, the analysis that we perform in this work package allowed us to state the relationships between the different conditioning and triggering factors for the 4 study areas. So as you can see, these are the parameters that we studied for all the study areas, and here we stated the different found relationship between them. Obviously, this information is of paramount importance for the future modeling that is going to be developed in the project. So, and that's all from my side. So thank you very much for your attention.
Thank you very much, Roberto. Now we're going to talk to data collection and sharing. It's going to talk Seyfettin Joma from Helmholtz Center for Environmental Research.
Okay, I would like to say, as we are running a bit late compared to the foreseen agenda, I would like to ask the 3 remaining speakers to adjust to the 15 minutes duration as much as possible. Okay, thank you.
Okay, hello everyone. So you hear me?
Yes.
Yes.
You see my screen also?
Yes.
Yes, we can see your screen.
Okay. Thanks a lot. So I will try to be fast. So my name is Seyfettin Joma. I am a researcher at Helmholtz Center for Environmental Research in Germany and also partner for InTheMED project. So today I would like to share with you what we are doing in terms of groundwater assessment at the regional scale, means at the MED regional scale. And the title of my talk, I adjusted a little bit to talk about the power of data sharing. The MED, I think when we started, it's clear one of the target of PRIMA also to have this kind of tailored solution in particular demo site transferable, and we can upscale them to the larger scale and the MED scale. And here the idea to see how much our regional scale in terms of Mediterranean also is aligned with basically our local solution. And the first observation was about the data monitoring and data sharing in the region by checking two stat, which the global fertility, the global groundwater work, and we can see the MED characterized by a lack of data sharing when we started developing the InTheMED project. And we believe also the data sharing should be happen on the right time, because if they are delayed so much, I think will result in maybe a wrong management strategy and probably a wrong decision. So as a team, we said that the MED regional scale deserve particular attention and should be considered as particular demo site, also similarly to the local demo site. I think groundwater usually recognized as a hidden resources because beneath the ground. However, its impact is very visible. And Marco this morning, he reflected the player that groundwater can do in terms of SDGs in general, either directly or indirectly. And in the South Mediterranean region, for instance, groundwater is the strategic freshwater reserve, which can buffer climate change, providing like sustainable water supply, ecosystem services. However, its budget becoming increasingly uncertain. And this also can result in lack of policy development. So I was lucky to be part of a team in 2018 when PRIMA appeared, where we investigate the Baltic Sea. So how much the Baltic Sea can serve as a time machine and as a model for future coastal ocean. And on that investigation, we tried to compare the Baltic Sea as a system to other sea, where the Mediterranean is one of them. And one of our observation was based on literature review that the Baltic Sea is had deteriorated in terms of anthropogenic pressure compared to the Med Sea, in terms of warming, increasing load, leaching, oxygen depletion, and the Med is ranked between the average and good status. However, in terms of readiness towards science-based management, we can see here using 4 indicators with research activity, monitoring activity, data availability, and governance structure. So the Baltic Sea is much in good position compared to the Mediterranean region. And one of the conclusions we got that the consistent and long-term funding are one of the key elements here to turn on this kind of red color to more green ones. So I think PRIMA is they will do great job there compared to the bonus program on the Baltic Sea. So it was clear enough when we started this idea that in-situ data is really lacking on the MED, and we have to give particular attention for that. And one of our targets was to create a long-term but the most comprehensive database in terms of physiometric level. The idea also to generate a product also to stakeholder, to gather data, to do analysis, but also come back to them and increase this knowledge production around the MED. So far, we are more than 15,000 piezometer collected. And here I will go through a different example reflecting the power of data sharing. So simply by putting all this in-situ data with historically measured and recorded, so it's not monitoring during the project, and simply by harmonizing them together, so we got like 5 direction or 5 idea how we can do it. So the first idea how we can do the trend and the clustering analysis of the groundwater level. Also, how much we can benefit from global groundwater gradient modeling around the MED, how remote sensing and the GRACE data can be used and tested compared to the in-situ data. Also, another example about the science policy interface and how much we can benefit from the success story and trend reversal observed in different demo sites. So the first picture was when we tried to understand the trend of the groundwater level around the MED. So we selected all piezometer which has more than 10 years of recording, and directly the total amount of piezometer reduced to the half. So only 7,000 piezometer respond to that request. And here we did some statistical analysis, and consistently we found that France, Spain, Italy, and Portugal, they share more or less the same statistics, where more than 60%, 60 to 70% of no trend, and we have between 15 and 25% of depletion. So here increasing means because we are dealing with water table depth. However, when we look at Turkey, which gathered only from open access report and publication, and we can see is outlier of that conclusion. So all of them is red, and simply because we don't have access to the whole national, and our conclusion is biased by local observation. So again, I think the first picture here, we can see a mixture of red and blue dots, and the message is not very smooth enough because we are combining piezometer level in different time period. So the next step, we focus on 30 years period in different time slots, and then the selection of wells go down to to less than 10%, where we can zoom and we can cluster. And we found we have 3 main clusters, so the constant trend, declining, and the recovery trend, which one of our PhD is working on that exercise. So again, also the hotspots, so we can see some hotspots, and we can also come back in the time and understand why and when this kind of depletion started. One of our target also to provide some controlling factor and the driver of this groundwater trends. And we have used 3 proxies, so precipitation, where the correlation is higher than 0.5, can explain maybe the recharge. Irrigation can explain maybe the overpumping, and the proximity to the urban area. And clearly that the constant, so the 3 first cluster constant one can be explained or highly correlation with precipitation, and the declining piezometer nicely can be explained by the proximity of irrigated area with 1 kilohectare. Urban proximity to urban is not explanatory variables here. So the second example was we recognize in the South Mediterranean still we are lacking in situ data, and the idea was how much we can use global groundwater modeling. There is now 3 well-known global groundwater model in terms of groundwater steady state but transient regime, and in collaboration with Sustained Cost, another PRIMA funded project, we are trying to evaluate the 3 model and see how much we can generate regional groundwater level steady state. And by doing so, we have used the Iberian Peninsula as our training and calibration and understanding site. And we have found that combination of model at global scale with in situ data provide better groundwater assessment at the regional scale. So the second example, or the third one, was, so this kind of gathering data together, we got a request from our colleagues with Horizon 2020 project, funded project, G3P, called the Global Gravity-Based Groundwater Product. And they are very interested using the groundwater collected data on the Mediterranean Sea to see how much the GRACE product, which NASA gravity recovery and climate experiment targeting groundwater storage anomaly, and our idea to see if we should at the district level at the groundwater system. And a methodology has been developed, and we found this kind of comparison should be done on the groundwater system. And here we can show the Dora River Basin in Spain, where we obtained very nice correlation from different products from GRACE satellite image. So the fourth example about the governance. So I think to do this water policy alignment within the MED, and we can see here clearly that the North Mediterranean area, they are complete in terms of water policy, straightforward and well harmonized. mainly due to the European Commission and directives, including the Water Framework Directives and other. And the south part, even though the Barcelona Convention appeared back in 1976, however, the policy are fragmented between the African Ministry Council for Water Creation and the Arab League, etc. And also this figure, I think, reflect also the data availability. I think when we have less data sharing, I think this kind of complex water policy scheme will continue. And one of the idea how much we can improve that. So how we can, and again, the Baltic Sea paper was inspiring for that idea, because the Baltic Sea, even though is not comparable in terms of size, in terms of processes to the MED. However, I think geopolitically and in terms of setting has experienced this complexity of the MED region of today, where the Soviet Union and the European Commission, like European Union at that time, should collaborate to solve the Baltic Sea problem. And we found that the Baltic Sea governance structure, which continuation of the Helsinki Convention 1974, where HELCOM play a crucial role on that, also supported by a group of scientists, can be translated to the Mediterranean region simply by using the element we have. So we have the Union for the Mediterranean, so they can play the role of the HELCOM. So we have the Barcelona Convention, can be part of the Helsinki Convention, and the group of expert MEDEC, I think, can serve, and other can serve as the scientific advisor of that. My final example is about the success story. So around the MED, we have very good success story, and simply by viewing that demo site or that experience, we can learn a lot. Here, the La Mancha Aquifer, for instance, the Eastern Mancha Aquifer in Spain, when we put the depths here, so we put the groundwater system. So here, all piezometer shaded in orange about the groundwater level on the region, together with the Yoga River, which connected to the groundwater. And only in 1994, when this kind of groundwater hidden problem became visible and the Yoga River went dry for the first time in the history, so big like mobilization from stakeholder, from local authority to create this user community, and the number of stakeholder involved and committed to the management, and they stopped this kind of severe decline, and even they gained some recovery. However, in the last few years, the climate change became another pressure. So my conclusion, I think the MED regional scale deserve a particular attention. Also, data sharing will open new horizons and alternatives where previously invisible. Reinforcement of systematic monitoring, data sharing, and regional modeling are mandatory towards science-based management. Tailored solution at local scale should go hand in hand with the regional scale investigation. The water governance structure, I think, can be improved simply by using all the elements we have around the MED, and with kind of activating process. So we have all the elements, I think, to move on with that. Connecting groundwater depletion with the driver also is very, very important, where we can create maybe a knowledge hub around the Mediterranean by joining forces together. As the next steps and the invitation, so the idea we can harmonize all gathered groundwater data from PRIMA funded projects, so this in the same repository. So then we can move from this theoretical aspect of data sharing to real action. And so far, we agreed 3 projects: Sustain Cost, InTheMED, and MEDSAL, to do it together. And I invite my colleagues also. We can dedicate a discussion for that. And our initiative is very, very flexible. So we can have the whole DFCR cause-effect chain for that, not only groundwater level. So it can be quality, it can be other proxy like soil subsidence, etc. So maybe also we can, at some stage, we can organize a regional stakeholder workshop where we can come back to our stakeholder and we show them what we get, what we observe, and we can listen from them also, and we can mix this local and scientific knowledge in better manner. So I would like to thank you very much. And if you have any question, please approach me. Thanks a lot.
Thank you very much. Now Manuel Pulido is going to talk about citizen science and ICT providing groundwater data. I will share my screen. Manuel, are you here?
Can you hear me?
Yes.
Okay. I'll try again to share the screen. So
okay.
hopefully this time it will work.
Yeah, we can see the screen. Yeah.
But it's
not yet. Okay. And
try with your screen if you want. If
yes.
not, I have your presentation.
We do. Yeah.
Okay.
Okay. So let's make a try. So it's supposed to be loading now.
Oh, yes, I think it's.
So can you see the screen?
I can see your screen, yes.
Now it's okay, yeah.
It's in a presentation mode, so you see.
Yes.
Yes.
It's perfect.
It's perfect, no? Okay.
Yes. Only 15 minutes, please.
Okay, yeah, sure.
Thank you.
I'll do my best. So thank you very much again, and thank you Cetaqua for I didn't say that, but for putting together the 4 projects in this very interesting webinar. So my presentation, I presented the project previously, the eGroundwater project. Now I will focus on the aspect of citizen science and ICT providing groundwater information. So first, starting with the definition of citizen science. No? So first, citizen science is the general public engagement in scientific research. And so the idea is we have to involve the users in collecting data and information. But it's very important in citizen science that we have a flow of information, not only from the users to the researchers, but in the other direction. So you have to flow in both ways. And this is very important because the users have to see the added value of their contribution to the project and to the research. Okay, so this is the way this is developed in this project. No, so the users will be helping in collecting relevant information on groundwater, but at the same time the project is sharing the results and relevant information also for a more efficient groundwater use with the stakeholders. The idea is to combine citizen science with ICT technologies. For example, now the tools that we have with remote sensing, and we have cases in which the most relevant groundwater use is irrigation. And right now, the method and technologies we have with a combination of remote sensing and agronomic modeling allow us to do an efficient assessment of irrigation water needs and irrigation water use. So this is very relevant. This is going to help us to improve knowledge and understanding of the aquifer, but also to improve the existing models, okay? Because with new data and information, we can improve the models, not only the groundwater flow models, but also the simulation of water management and groundwater strategies. And at the end, and through a participatory process, the idea is to enhance, to develop and enhance more sustainable management strategies for the aquifers. Okay, so
Manuel, yo creo que no están pasando tus transparencias.
You can. Oh, thank you, Jaime. Okay, so you don't see the slides. Move on.
We are always seeing the same slide.
The same slide.
Oh. The title, yeah.
So let me try again to. Okay. So can you see?
I don't know why, but I can change your slides by myself. I don't know why, but I can change your slide. But maybe, yeah.
You can do from there. Okay, so can I ask you to move the slides for me?
Yeah.
But I don't see any change. Eh?
No, I don't see them either. So probably the slides were, yeah. So let me share again the screen.
Yeah, share again. Let's try.
Yeah.
You can share the PDF if you want.
Yes, can you share the PDF, Beatriz, please?
Yes.
I think that's the best solution. Thank you.
Sorry, Manuel, because I could see that under the slide there was like a function navigates forward. So I don't know if now you can do it.
Can you see my screen now?
Okay. Yeah. Thank you. Yes, we can see the slides shared by Beatriz. So that's, yeah. I think that's perfect.
Let's do it that way. Yeah.
Okay. Thank you. So Beatriz, can you please move to the next one?
Yes.
So yeah, that's the one I already explained, no, about the combination of citizen science and ICT technologies to improve knowledge of and understanding of the aquifer, and at the same time improve models and to use all this in a participatory process to improve the groundwater management strategies. So can we go to the next one, please? Okay, so let's see one example of how we are doing this. I will focus mainly on the case study in Requena Utiel in Spain. This is a groundwater basin, groundwater body that is within the Júcar River Basin, and is also shared by chance with other PRIMA projects in the Med. In this case, the main groundwater use is by far irrigation, and it's irrigation of vineyards. So in this case, the idea was to use this combination of citizen science and ICT technologies to produce better understanding and better information on groundwater use and groundwater management. So the first thing we are using is agricultural modeling combined with remote sensing. We are going to do that to improve estimation of crop water use, irrigation requirements for specific plots, and also to provide advice to the farmers in efficient irrigation practices, combining these tools with forecasting services. Can we move to the next one, please? Okay, so I'm going to briefly explain the approach we follow. So in estimating the crop water needs, the main inputs are, on the one hand, we need to use the land use data. So we use the land use data in order to classify the crops and develop crop maps. And on the other hand, we are going to use agroclimatic observations. So basically, we use the rainfall, and we use also different meteorological variables that are needed to estimate the potential evapotranspiration of the crops. Then at the same time, we are using optical remote sensing images coming from Sentinel-2 satellite. This is part of the Copernicus program. It's a program that, as you know, is headed by the European Commission in partnership with the European Space Agency. So by using those Sentinel-2 images and processing them, we obtain the vegetation index, the NDVI, and using the right algorithms, we determine, together with the observation of land use and agroclimatic observation, we estimate distributive maps of crop coefficients for the crops. And just by applying FAO 56, we can determine the irrigation needs. Okay, so we have the crop irrigation needs, and we are using this mobile and web application to share this information in real time with the irrigation users. So can we go to the next one, please? So we can do that at different scales. So we are doing this analysis at the aquifer scale. So we can estimate the crop water needs, and even if we are talking all the time about the same crop, because the main crop by far is vineyards, we know that you have different varieties of vines, you have different soils, you have different particular local conditions, different crop management as well. So there are different crop water needs spatially. So we can do this analysis at the aquifer scale with the crop water needs. And next slide, please. But we can also do the analysis at the plot scale. So just by using the mask with the perimeters of the different plots that we have in the irrigated area, we can estimate for different irrigation periods, we can estimate the crop water needs at the plot scale. And this is information that we are going to share with our groundwater users through a mobile app in which we have an exchange of information. They are sharing information on their plots and their pumping wells, and we are sharing information on their water needs and water use, and also on the status of the aquifer, so that they can know this in advance to better manage groundwater in the system. So can we move to the next one, please? A first thing here is that, as you know, vineyards can be irrigated or can be rain-fed. So a first need was to have a precise estimation of the spatial variation of the irrigated area. So we did also with satellite information, and we have paper under review on that, and with high accuracy, we were able to develop an irrigation mapping of the area and clearly identify in which plots the vineyards are irrigated or not. That this is done by a combination of satellite, multispectral images, and artificial intelligence, in this case, machine learning. Can we move to the next one, please? Okay, so a first step is the estimation of crop water requirement, but the other steps is the estimation of the real crop water use. What is the actual crop water use? For that, we are using energy balance, surface energy balance algorithms that called CEVAL, with combination of with remote sensing. But in order to calibrate this information from satellite, we need a special device. So if we go to the next slide, Beatriz, please. So this is what we show here. So we are using eddy covariance in the field in order to have a better assessment of the energy balance at the plot scale, and do this for calibrating the images that we are getting from the satellites. So we are using this in order to estimate actuality, okay? And we can estimate if the crops are stressed or not. So what is the degree of irrigation stress? And this is useful information to determine what is groundwater use in the area. This is very important because this is an indirect assessment of groundwater use. A similar approach is also done in Mancha Oriental. And this indirect approach, we want to contrast this information with the information provided directly by the stakeholders using the mobile app. So we are asking, one of the questions we are asking them is how much groundwater they are using for irrigation, but we want to do an indirect assessment to see how if they both agree or not on the estimation. The next thing is to put a weather forecast facility on a weather forecast. Combine this with weather forecast. Can we go to the next one? Yeah. So the forecast is very important. Why? Because if we want to produce relevant information for the farmers, they need to know how much water they have to use for irrigation in advance. So we are combining two types of forecasts. We are doing short-term forecast. This is up to 7 days. So this short-term forecast is going to send the farmers information on irrigation water needs at 1 week, and we are also testing the possibility of 2 weeks in advance so that they can organize the irrigation. And second, we are going to provide weather forecasts at the seasonal scale. So can we move to the next one, please? So the seasonal scale is also very interesting because groundwater management strategy in Requena-Utiel right now is based on this. They have three types of year: dry, wet, or normal year. And depending on this classification, the River Basin Authority is allowing the farmers to use a certain amount of water for irrigation. Okay. If we have a tool to predict the type of year in advance, farmers, they will know in advance what are the conditions they will face in their crops, and the water agency will know in advance how much groundwater will be used. Combining this prediction with groundwater modeling, we can also have an assessment of the future evolution of the aquifer in the next 6-7 months of seasonal forecasts. For that, in the seasonal forecast, we use Copernicus service, and we have a prediction of meteorological variables in the coming 6-7 months. We have also prediction of the type of year according to the rules, but also we are using hydrological model to transform meteorological prediction into groundwater recharge, which combines with groundwater model can predict also groundwater levels. So can we go to the next slide, please? Well, so as I said, depending on the type of year, the farmers have a maximum allotment of water for irrigation, dry, normal, or wet year, and this can be predicted, and we are testing what is the skill of this prediction using seasonal forecasts. Can we go to the next one, please? Basically the results I have shown correspond to, as I said, corresponds to the Requena-Utiel case, but we are also extending the analysis to the other cases because the satellite information is already available. They have different crops, so we have small changes in the algorithms adapted to the local conditions, but this is going to be produced for the 4 cases. Can we go to the next one, please? Okay, this is a tool I mentioned this morning. So this is a mobile app that is going to share with the farmers. We have a first version of the app that is being tested by some of the farmers, a selected group. Can we go to the next one? And there is a combination of information on the plot scale and also the pumping wells that is going to be provided by the irrigation districts in some cases and by the individual farmers in other cases. Can we go to the next one? I can show a few. Next one, please. I can show a few mock-ups. So, for example, we do have a declaration of a borehole. Automatically, we are including all the pumping wells that are officially included by the water agency. This can be also done just by taking a picture of the well, and it's automatically located in the GIS. But you can also declare your own well, and also to have information on groundwater levels measured in a specific well and groundwater use. Can we go to the next one? So this is a combination of providing information by the user, so information on the irrigation plots, information on the pumping wells. This information is a bit adapted to each of the 4 cases because the conditions are a bit different or the context is a bit different. And also at the same time, the farmers are receiving, through the same application, are receiving information on their irrigation water needs and the evolution of groundwater levels. So in next slide, you can see that this is a type of information we are considering for the mobile app, so they can follow in real time what is the current situation of the aquifer, but also the future evolution, combining seasonal forecasts and comparing groundwater levels at their plots with groundwater levels, historical groundwater levels, so that they see what is the situation of the aquifer in this irrigation campaign. So can we go to the next one, please? Okay, I know the time is almost over now, but we are combining this with other information strategies. For example, in Morocco, they are developing locally made water measuring probe that has been developed in Portugal. Is something that can be easily produced at a very, very low cost, and is going to be useful in Morocco for measuring groundwater levels in the wells. Next, please. And the mobile app and the web server are going to be implemented and adapted to the 4K studies in 3 different languages, so that we make sure that this is user-friendly to be used by the different stakeholders. Next, please. So just conclusions. We are testing the potential role of citizen science combining with ICT technologies to improve groundwater data and information. And second, we want to see how much this improvement can contribute to better groundwater assessment, better groundwater models, and finally, to improve groundwater management strategies, what of course has to go through a participatory process with the relevant stakeholders. And that's the presentation. Thank you very much, and I remain at your disposal for any question.
Thank you very much. Now it's time to explain groundwater governance and groundwater sustainability by Emilio Custodio from Universitat Politècnica de Catalunya. I'm going to share my screen with the presentation.
Yes. Yes.
Okay. Can you see my screen?
Okay, here it is. Good morning to everybody. Well, I will present some recent achievements on characterization of governance of groundwater. This is a project that was charged by Cetaqua to our group in the Polytechnical University of Catalonia, and I will try to explain as short as possible the contents of this report. Next one, please. Next. The title is Groundwater Governance and Groundwater Sustainability Evaluation Index, application to 8 diverse Spanish aquifers and the results. These 8 diverse Spanish aquifers are called the pilot areas, and we will refer all the results only to these 8 aquifers. Next one, please. There are many definitions of governance. I don't like to spend too much time on this. This is one of the definitions of governance that I like more, but there are many others. What is important is that we have to take into account the environment and the services provided by the environment. We have to talk about the scale of the problem, and in the bottom is also to relate the scale of the real problem to a higher level of governance. There are 2 scales to be considered. What dominates is the economic, social, legal, and administrative framework, but science is important as a basis, but not decides. Also, traditions, local ways of doing things are very important, and we have to take into account some ethical and moral principles that affect mostly people and not so much institutions. Next one, please. The water governance has several components. As I have said, science and the knowledge of the system, including the uncertainty that is very important, are the basic pillars. But what is really important for the decision about groundwater use, groundwater management and water governance is that if there is or not integrated groundwater resources management, and as I said, the economic and social context, the law and regulations, even if the law is not adequate, the water administrations that in many cases go against what is generally admitted as sound governance and the traditions and habits of water. Water governance has to consider that water is scarce, that is needed in a given time and in a place, is a human right, can be degraded, and degradation of groundwater usually is the key important problem currently and will be dominant in the future, that water cannot be changed, cannot be replaced by other natural resource, and as we can suspect that groundwater is not only needed for the present, but also is needed for the future generations. And this is very important because groundwater changes very slowly. Next one, please. Why we talk about groundwater governance? Because groundwater is not visible, but is well known. Groundwater flows, but slowly. People, it's difficult that they realize really how slowly flows groundwater, but it flows. And also transport dissolved substances. It transports mass in large quantities. Flow is very slow, but it's in the whole territory. Then large quantities of mass can be moved. And groundwater is not isolated. It's intimately related with surface water, both in quantity and in quality. And what is very important is that the relationships between surface water and groundwater is dependent on the aquifer exploitation status. Then, when we talk about groundwater governance, we also to consider surface water governance and the joint governance of both aspects of water in the water cycle. We have also to be taken into account that groundwater is essentially heterogeneous. Residence time is very long. There are uncertainty, and we have to know and we have to deal with uncertainty that, as has been said before in some of the presentation, monitoring is needed, but it's expensive. Then the groundwater is a common pool resource that is a difference with other natural resources, that pollution is a very slow process and contamination is almost irreversible. Next one, please. Then groundwater is needed to guarantee the human right to water for human well-being and to sustain food production, sanitation, and economic activities. And until now, the exploitation has been largely uncontrolled, and it has created a lot of problems in many areas. It doesn't mean that groundwater is not important. Groundwater is essential, it's important. The only problem that we are in the early development, and in the early stages of development, there are always some lack of control. It can be controlled, and they can be corrected, and in the future groundwater will play an essential role in water resources. Groundwater abstraction should be sustainable. There are some indirect effects, say some damages that has to be bearable. They have to produce a net benefit to society. We have to consider externalities. This is something that is usually not taken into account even by the water administration. And to do this, I insist, we need knowledge and monitoring. Even if it is expensive and has to be permanent, and it has a cost that somebody has to be paid. And this somebody is the government as providing information for science, for technology, but also by those that are receiving the benefits of using groundwater. Then the user has also to pay monitoring. Next one, please. This report is divided in 15 chapters, and these 15 chapters, there are some ones that are introductory ones. One is to present the tool that is used to the evaluation. Then there are the 8 pilot areas, and finally a summary and conclusions of the full report. Next one, please. Then groundwater management and governance have, as I said before, at least 2 scales. There is the scale of the problem and a broader scale, and is necessary to consider both. But the point of view can be and should be generally different. But for this governance, there are several barriers. One is poor knowledge. The other is malfunctioning of regulator. Many times there is not a real independent regulator. People is not available that groundwater is a common pool resource. This is a lack of leadership. The water administration in many cases are authoritarian. They try to control everything without the stakeholders, and sound groundwater governance need these stakeholders as one of the key elements for success. And in many cases, there are political interference that we have to measure in some way to evaluate the degree of good governance. Next one, please. Then what we try to do is to look for a governance index, and this governance index is something that is good for the administration and allow comparisons. Then is something that in many cases is wanted, but the intrinsic value is low, as it is impossible to condense in a figure the complexity of the real world. There are many attempts by several experts. This is explained in one of the chapters. But even these attempts, there are several focus. Then, depending on the focus, the index is different from one author to another. It is useful to have an index to systematize case analysis, but comparisons need to be done with caution, and they are not useful directly for decision making. This is only something that to help, but not for this decision making. We have to consider hydrology, hydrogeology, management, administration, and governance. And we have to consider something that is not in other water resources, that is the time of renewal and the time of response. Renewal is not the same as response, and we have to consider both of them because, as you know, groundwater has a volume that is much larger generally than the total annual recharge, and the response times depend on the kind of aquifer. It is a water table aquifer or this a confined aquifer, and the response times can be from days, in many cases up to centuries. Then this is something that is outside the normal way of thinking of people working with water. At case scale, we have to consider the integration into a broader scale, and what is important and is new is that quantity issues, well, it can be, we can find indexes more or less useful, but quality issues are very difficult, and to get a quality consensus that is essential from sound governance is sometimes very complex and difficult, and in some cases it cannot be done easily or cannot be done at all. Next one. We propose an index that it considers different elements. One is the exploitation index, that is the normal exploitation index of pumpage respect recharge. But this is not enough because in many cases we are using reserves. When we are using reserves, we have to consider these reserves and include in the exploitation to get an expanded exploitation. This is done by considering that in many cases with pumpage, we don't affect all discharge of the aquifer. This is typical in islands in which we have water exploitation in the top of the island, and it's also important in coastal aquifers. Then we correct the exploitation index, taking into account the quantity of water that we cannot control and we continue to be discharged. We have the index of water stress, that is the exploitation index corrected by the use of reserves in the aquifer. I'm sorry, because there is a minus sign here and must be a plus sign. We correct all this, taking into account the impact of in quantity of discharged water, the impact of quality of surface of discharged water, the ecological effects, the impact of non-agricultural supply warranty, the impact of agricultural supply warranty, and some negative geotechnical effects, and we have heard about this a few moments ago. Then there is terms average that corrects the exploitation, the water stress index to a new corrected index of exploitation, taking into account not only the effect of using reserves on discharge out of control of pumpage and these other correction terms, and with this we have a first index that we call index of groundwater use stress. Next one. And the governance index, it is composed on topics, that is a series of questions are grouped in categories, and the categories grouped in groups. Each topic is given a score from 1 to 5, and the category is obtained by the average of the topic scores with a correction value that takes into account that when the topics are close, the topics in the category are close to each one, it means that we are in a compensated system. But sometimes there are very high and very low scores, and we correct this, we correct the skewness of the distribution with a system that tries to get easily an approach for the standard deviation, and we correct the value by subtracting the standard, the estimation, the course estimation of the standard deviations. And there is a group value that is the average value of the category value. Then with this we get a corrected governance evaluations, and then we propose to use 3 figures for index. That is the stress index corrected, the management index that is one of the categories, and then the corrected groundwater index. With this, the next one, we apply this to these 8 pilot areas, and the results. Next one, please, are given in this table, and time doesn't allow to go to them, but if you look at the surfaces, it's very variable. There are coastals, there are in the inner part of the Iberian Peninsula, there are islands, there are in some cases very, very small areas. In areas there are with large population, activities can be also varied from agriculture to industry, with different influences in the local economy of the primary sector of agriculture, corrected or not, with the secondary effects on services sector, and the number of groundwater bodies officially existing in the area. We also make an estimation of the renovation times or renewal times in the aquifers, and then we have the stress index we have given here, and here there is a result that, you can see that, by example, the corrected in the stress index varies from very high to low in some cases. But these low values has to be corrected because in some of these cases, the yearly values, they give there is no water stress at all, but there is a seasonal water stress that can be very important. That it means that what we are proposing is good for average values, but if we consider that there are very seasonal, important seasonal variations, then the index is not valid at all. This next one, please. Here you have here an idea of the stress management, governance, and corrected